And we are now recording. If I can get the slides to respond, which they're not doing very well. There we go, finally. I don't know what it's doing now. Okay, let's try it one more time. There we go, finally. Okay. There is one additional announcement I need to make, just to well, you haven't heard it yet, but just to so you'll be aware. Normally on Fridays I have office hours 7:45 to 1 o'clock, okay, on Birmingham campus. I wasn't there this past Friday because I had the treatment. And I won't be there this coming Friday because we've got math meetings down in Opelika at Southern Union College. So we'll be leaving very early Friday morning, and I'll be gone all day and coming back fairly late in the evening on Friday evening. So no office hours Friday again. And then looking ahead, the following Friday, if I'm not mistaken, I have a doctor's appointment, okay? But it's at 8 o'clock, and I hope to be through with that by 9 and probably back on campus by 10. So I should be there for the last part of my office hours on the following Friday, but I won't be there. I wasn't there last Friday. I won't be there this Friday. And I won't be there at the beginning the following Friday. So hopefully I'm getting all these out of the way, so we'll move on from there. Next, any questions on anything we've covered so far? All right. Now, where my mark was that we had just been talking about multiplication by the identity matrix, okay? And we had an example 6, and then for some reason, all of a sudden, they had a whole new concept, no break, no subtitle or anything else, and they started talking about for repeated multiplications of square matrices, they have to be square matrices, use the same exponential notation that we use for real numbers. And we went over that, and it says it's convenient, this is on page 56, just above the middle part of the page, it is convenient to define a sub 0, and this may be why they brought it up here, I said sub 0, a to the 0th power to be, and remember a is a square matrix, n by n matrix. What do you think a sub 0 would be then? The I matrix of that dimension, I sub n. You're absolutely right. A to the 0th power, meaning just like 7 to the 0th power is 1. Well, in matrices, a matrix to the 0th power is your identity matrix, which is like, sort of like the number 1. Okay. These definitions allow you to establish some other properties, such as this one. A to the jth power, let me make sure I get my subscripts the same way they do, times a to the kth power. How do you reckon we would do that? J plus k, absolutely. For some reason, the pen's not right. There we go. Okay, to the j plus k. And that follows just like it does from real numbers that I'm liking 7 today. 7 to the 3rd power times 7 to the 5th power would be 7 to the 8th power, because it would be 7 times 7 times 7 is 7 to the 3rd times 7 times 7 times 7 times 7 times 7, 5 times, and that's a total of 8 times. Same thing here. A to the jth, as long as A is a square matrix, if you multiply that by itself j times, and then multiply that by itself k times, you've got a total of j plus k times. So yes, that follows pretty directly. And secondly, again, just like you see in real numbers, a to the j raised to the kth power would be a to the j times k. Absolutely, because you'd have if a times a times a times a j times, and then that raised to the kth power, you'd have that k times, and that would be j times k. And of course, that would be the same thing. Okay, now, so let's move on to example 7. I think I'll erase everything that's here because I think we're going to need some room. For the matrix A, little square matrix 2, -1, 3, 0. Okay, what we want to find is A cubed, which of course will be A times A times A. Okay, A 2 -1, 3, 0 times 2 -1, 3, 0 times 2 -1, 3, 0. Okay, and you can do these, remember, in any association that you want to, and since they're all the same, actually any order you want to as well. But let's do what you want to do. First two. Okay, when you do the first two, what size is that going to give you? 2 by 2. So we got 1, 2, 3, 4 places. You start telling me what to fill in. First row, first column, right. One, right, okay. Next. First row what? We just did first row. Second, okay, second column, okay. Oops. -2. Next. Six. Next. -3. And multiply that by 2, -1, 3, 0 again. And what size will that give you? 2 by 2 again. Okay, where do you begin? First, okay. Yep, -4. -1. 3. -6. Very good. Now, there's no way you can look at that and say, yeah, I know that's the right answer. You have to just trust your work. But if you look in the book, that's what they get. Notice it's not, and don't ever think it would be, raising each entry to the third power. That's not how you do matrix multiplication, so don't even go there. Okay, that doesn't work. All right, very good. Now, they're referring you back. Sorry, my eye is just stinging like crazy. In section 1.1, you saw that the system of linear equations must have exactly one solution, or infinitely many solutions, or no solutions. Only 3 options you can have. Okay? Now we can use matrix algebra to prove that, and that's what theorem 2.5 basically is approaching. And here's what it is. For a system of linear equations, precisely one of the following is true. Exactly what I just said. It's not even worth writing down. The system has exactly one solution, has infinitely many solutions, or has no solutions. Now, it is an interesting little proof there, okay? And if we weren't probably a little behind where we need to be, I think it would be worth doing. But definitely read through the proof. It's pretty straightforward. I don't think it's a a difficult thing to do at all. Let's just at least read through it. Represent the system by AX is equal to B. Some matrix A times your variable column vector X is equal to some column vector B. Okay? Now, that's your system of equations. Notice they haven't said anything about size of A. It doesn't have to be square. Nothing. Okay? But anyway, that's your system. If the system has exactly one solution or no solution, then there's nothing to prove. Okay? And that's sort of a strange statement, isn't it? You're trying to prove this, but if it has number 1 or number 3, there's nothing to prove. Okay. Whoa. And that leaves me a little empty. You know, that seems like you need to at least prove that statement's true. But so assume that the statement has at least 2 distinct solutions, x1 and x2. Okay? You're going to assume that it has 2 different solutions, x1 and x2. x1 would be some column vector with however many entries that would have. x2 would have another identically sized column vector with different entries. At least one entry has to be different. If you show that assumption implies that the system has infinitely many solutions, then the proof is complete. Because x1 and x2 are solutions, we have that from here that a times x1 is equal to some b1. Okay, we don't know what it is, but it's some value. Okay. I'm sorry, we don't even need a b1 there. Okay. All right, here we have, both of the Williams brothers are here. Okay, in fact, I forgot to mark you, so I get to mark you now. Duh. I put the dates in and then forgot to put your presents in. Now this, I think, is the first time Emmanuel's been absent, so that's strange, but let's go on. That leaves, Nigel is the only one who's not had an absence yet. Way to go. All right. And maybe he'll still be in. So if x1 is the solution, ax1 is equal to b. If x2 is the solution, then we also have, this is on page 56, the proof at the bottom of the page. I was going to do it because I thought it was going to be fairly quick, and now I'm beginning to have my doubts. Okay, oops, that's supposed to be x2. The ax1, we've assumed that x1 and x2 are two distinctly different solutions, and what we're trying to show is then that means you have to have an infinite number of solutions. Okay? Now, if you subtract this from this side, okay, minus ax2, okay, then this goes away, and this says that a times x1 minus x2, okay, is equal to 0, okay, because you subtracted it from both sides of the equation, okay? Now, this implies that the non-zero, now remember, these are distinctly separate, different vectors, different solutions. That was our assumption. These are 2 distinctly different solutions. So if these are distinctly different, then this thing cannot be 0, can it? Because they're different. Well, from what we did before, when you have this times this equals 0 vector, and this is a vector, remember, this is just like your B was, that's a 0 vector here. That means if this is not 0, A has to be 0. But we assume that A wasn't 0, so let's see. Okay. So this would say that let's see, how are they getting from that to the next step? This implies a non-zero column vector, which is that difference there, and what they're calling this is x sub h, and that's going to be a homogeneous, that's where the h comes from, solution that says that a times x sub h is equal to the zero vector, okay? Now, that's a solution for a homogeneous system, ax equals 0, not c. So for any scalar c, then a times x1, that first one that we had here, plus c xh, okay, is going to be ax1 plus a ca x sub h. All right? That's just distributing a across two vectors, okay, which is a legal move. Well, this is your b, okay? We had that from the very beginning, okay? And this is obviously the zero vector. C times this is a zero vector. That's going to be 0. So that says that a times x1 plus any arbitrary c, any c that you chose to put there, times that x sub h, okay, is going to also be a vector. I mean, a solution. Which means that you have an infinite number of solutions. So remember, we started with the fact we had two distinctly different solutions. And Jonathan's here. Good deal. Just missing one. Usually he's here early, so I'm guessing he's not showing today. Too bad. We'd love to have perfect attendance. We are doing the little proof at the bottom of page 56, okay? And this I thought was going to be a lot simpler. And it is simple, but it's basically you get to the point of saying that, therefore, if x1 is a solution and there's some other uniquely different solution, x2, then this is saying that means there's an infinite number of solutions, and we've just basically proven that. Just wanted to do it so you get an idea how they go about doing these proofs. I don't know if you'll ever take another linear algebra course, a higher level course, but I almost guarantee you if you do, they'll have a lot more proofs than what we've been doing here, okay? So just to get you ready for that. But are all three of you engineers or you math? You're math. So you might hit a few more of these. So the other two are engineers, right? Pre-engineering. I doubt if you'll see that many more, hopefully. I mean, I didn't say that. Okay. Now, before we do the transpose of a matrix, let's do a discovery. This book likes these things. A lot of the current texts do. Let's see what we can determine from this discovery. Here is a matrix A, okay? Their favorite 2 by 2, 1, 2, 3, 4, okay? Now, here's a matrix B, maybe one that's not quite so favorite, but 3, 5, 1, negative 1. Just some other old matrix B. Now, ooh, I really hate when they do this. They give you the discovery before they tell you what the definition is. So we're going to hold off this and do the definition first. We haven't done transpose yet, have we? Okay, I didn't think so. The transpose of a matrix is formed by writing its columns as its rows, okay? So, for instance, if A is an m by n, matrix, okay, then it would be represented like this. Give me some of those elements. A sub 1, 1, A sub 1, 2, A sub 1, 3, dot, 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 up to A sub 1, N, because there's N columns, right? Second row would be A sub 2, 1, A sub 2, 2, A sub 3, 2, 3, dot, 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 up to A 2N. A sub 3, 1, A sub 3, 2, A sub 3, 3, dot, 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 up to A sub 3N. And for those who just came in, if you notice I'm up here blinking a lot, I've got conjunctivitis in this eye and it's really stinging like crazy. So it's sort of hard to focus. So if I get a little off, you'll know why. Let's dot, dot, dot this down to the last row. What would the last row be? A sub what? Now M1, right? M2, M3, dot, 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 over to AMN, N, okay? Dot, 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 everywhere, dot, dot, okay, everywhere, okay. Got it? Now, the definition of a transpose of any matrix, any M by N matrix, would be not an M by N, but the A transpose is now going to be an N by M, because what we're going to do is interchange the rows and columns. So whereas this was a row here, that becomes a column. A11, A12, A13, that first row becomes the first column. Dot, 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 down to A sub 1N. Okay? Then you have, give me the next one. 2, 1. Now, you want to go right or down? I don't care. Say which? Down, okay. 2, 2. 2, 3, dot, dot, dot. 2N. Next. A31, A32, 3, 3, dot, dot, dot. 3N. You got it. Then dot, dot, that across, and what would you have as the last entry on the first row? A M1, a M2, a M3, dot, 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 everywhere, dot, dot, down to a M N. There's something wrong here. No, yeah, it looks wrong, but it's okay, because your M is now representing your column and your N is representing the row. So it's the backwards from how we usually say it, but it is true because that's the transpose. We did things like this. We now have N rows and M columns. Even though the order is like we usually do, that's what we've got here, because you see we've got 1, 2, 3, 4, 5, 6, 7, up to N rows, N rows, N rows, N rows, and 1, 2, 3, 4, up to M columns. So we have reversed the M and the N, though the entry looks like it's the same, and it's the same entry that was here, but it's now, that doesn't represent row and column. That's what a transpose is. All right? It's an N by M. Okay. Now let's get back to the discovery. Okay? And see what we can discover about these two matrices. sorry, they gave you the discovery using something they hadn't given you the definition for. So I thought, let's give the definition first. Now, notice here, what size did they give you? 2 by 2. So these will be perhaps a little more straightforward than an n by m by n, because they have the same number of rows and columns. They are square. Okay, but let's see what we can determine here. It says calculate AB transpose. Okay, what are you going to do first? Multiply A times B. So let's do that. What size will that be? 2 by 2. Not going to be too hard to do, is it? Where do you begin? First row, first column. What would that give you? Say again. Okay, first row by first column. Say again. Hi. Okay, okay. Okay, we're changing at the line. Okay, you got a 3 plus 1 is 5. You hit it. Yeah, right. Okay. All right, next. Which way are you going? 1, 2. Okay. What would that be? Ooh, wait. Let's start over. Multiply and add. Okay. What are you doing? Tell me, which entry?
I was doing like 24.
Which?
I was doing like 24.
I can't hear.
Like 2, 2.
2, 2? Oh, you're going down to this one.
No, I mean like 2, 1.
Oh, 2, 1.
Yeah.
Okay, that's what I was trying to figure out. Where are you? Where are we, Waldo? Okay, where are we? 2, 1?
Yeah.
Okay, let's do 2, 1.
It would be 2 times 5, right?
5.
Which is 10 plus 4 times -1.
Okay. All right.
How am I doing it back?
Okay, is this the one you're doing?
Right.
2, 1. 2. I'm sorry. This is 1, 2. Or were you doing 2, 1? I'm sorry. Which are you doing? 1, 2 or 2, 1?
2, 1.
2. Oh, you're doing down here. Okay, I'm sorry. I thought you were saying the other. Okay, yeah. What do you get?
You would do 2. You would do 2 and 4, right? Times 3. No, 2 and 4 times 3 and 5, right?
Okay. If you're doing this entry, that's first row by second column. Okay. So that would be
2.
which would be
3.
3. Is that what you were saying before? I wasn't hearing, but yeah, that's a 3. Now, if you're doing the 2, 1, that would be okay. 2,
3 and
1.
4. Okay.
Ah.
So it'd be
3
times 3, which is 9, and 4 times 1, which is 4, which is
13. Excellent. Okay. And the last one would be 11. Excellent. Okay. Yeah. You. I have to use my hands. I mean, no way around. That is AB, but we want the transpose of that. So what is the transpose of that? Five. Where does 3 go? Down. Okay. 3. 13, 11. Okay. You have to tell me which way to go on those, okay? You could have said 5, 13, 3, 11. That works too, yeah. Just tell me which way to go. I won't always go there, but yeah. All right, so we've done the first one. Now, they also say do A transpose times B transpose. Okay. Now, what is A transpose? Whoa.
Are we still using like the A and B over there?
Yeah, those A and B up here.
So it would be 1 and 2.
Going what? Down, yeah, 1, 2. 3, 4 going down. Times, and what's B transpose? 3, 1 going across. 3, 1 going across. 5, negative 1 going across. Very good. Okay, let's multiply those two together. What size will that be? 2, 2. Okay. And what will that give us? $18. Got it. Okay, next. Negative 2. Next.
6 plus
26. Okay. And how about negative 2? Okay. Very good. All right. So, those don't look anything like each other. But then they say do this. Do B transpose times A transpose. Now, we've already written what those are, but just put them in that order. 3, 1, 5, negative 1 times a 1, 3, 2, 4. Okay? Now, let's multiply those. What size is that going to be? 2 by 2 again. We're stuck there, aren't we? So, let's see what we get. 5. 13. 3. 11. And guess what? It's exactly that. So what this is suggesting, not said for sure, that AB transpose is the same as the reverse B transpose A transpose. So you don't just carry the transpose across. Now don't confuse a transpose with a power. Those are different things. That's a letter, it's a symbol, it's telling you an operation. Power is doing a different operation, but not the same. But this is saying reverse the order and multiply the transposes together. And sure enough, it appears those will give the same result. Okay? So, let's do, we'll come to that later. They like the discovery for you to discover it yourself, and then they'll tell you about it later. Okay? So find the transpose of each matrix. Here's a matrix A, 2, 8. What would be A transpose? 2, 8 going across. A column vector, 2, 8. Very good. Okay. Let's do the B one. B is a big old 3 by 3. Very creative one too. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sort of like Sudoku or something like that. Okay? What would be its transpose? Yeah. 1, 2, 3, 4, 5, 6 going down. 7, 8, 9 going down. Okay. Very good. Let's do C. Another 3 by 3. it's a 1, 2, 0, 2, 1, 0, 0, 0, 1. What would be its transpose? Okay, say again. 1, 2, 0 going across. 2, 1, 0 going across. 0, 0, 1 going across. And guess what? Those are the same, aren't they? Whoa! Okay. Now, do you notice anything special about C and C transpose? Yes, symmetric matrices. They've got the same main diagonal, yes, and the off diagonals are exactly the same as well. Okay, this is this, this is this, that are the same. Wow. So yeah, that would be the same. Now, the main diagonal, they don't all have to be the same number. They all have to be ones. That's the case they are, but it could be 1, 7, 14 or 1, negative 3, 85 or anything else. Those positions don't change as long as the off diagonals, do change. I mean, are the same. Okay. So sure enough, that's a special one. How about D? Matrix D is 0, 1, 2, 4, 1, negative 1. Does it have a transpose? And what was that be? 0, 2, 1, 1, 4, negative 1. Yeah, very good. Okay, let's see if they got them right in the book. They got the first one, good for them. They got the second one, even better for them. They got the third one, wow, they just copied the first one, okay. And then the D transpose they got right too. Good for them. So, that's what a transpose is. Let's give some properties of transposes, which at least one of these we've already seen. Okay? Whoa, that's not what I wanted. Okay. Yuck. Goodness, my eye's stinging. It hurts. Okay. If A and B are matrices with sizes that give the given matrix operations are defined, okay, and C is a scalar. So A and B are matrices, and I'm going to put properly sized. You know what that means? That, goodness, my eye stings, okay? I'm sorry. And C is a scalar. Okay? Yuck. Now, I'll write down. What do you reckon A transpose transposed is? Say again? Okay, you're starting with a matrix A, whatever size it happens to be. Then you're transposing it. And then you transpose it again, you get back to A. Exactly. Just what you would expect, and it is indeed true. The transpose of a transpose is its original. Okay? Now, number 2. If you got A plus B transposed, what do you reckon that is? Plus B transposed. You can do it with addition. Remember, addition follows most of the same rules that real number addition does. It's when you get the multiplication, you can't, okay? But with addition, yeah, that follows just like you would expect. The transpose of a sum. So the first is a transpose of a transpose. I'm going to write transpose as expose, okay? X usually means trans, okay? Okay? The second is the sum, the transpose of a sum, okay? Number 3, the transpose of a scalar multiplication. What you reckon that's going to be? A transpose, you got it. So the transpose of a scalar multiple. And then 4, goodness gracious, the one that we showed in our discovery, AB transpose is going to be, yes, remember with multiplication, the rules don't follow as nicely. B transpose, A transpose. But there are rules, okay? And that's the transpose of a product of two matrices. Okay, remember, for sum of two matrices, transpose, just like you would expect. The transpose of a transpose, hopefully what you expect. Transpose of a scalar multiple, just what you would expect. It's the multiplication that changes because now you have, goodness gracious, you have to reverse the order. But if you think about this in terms of dimensions, and I always find this helps, okay? Remember, A and B are not necessarily square. They could be not any sizes, but a variety of sizes. So give me a size for A. Make up a size with letters. JK. So A is going to be a JK matrix. Now, what must be B? K something. Pick another letter. I. Okay? KI. Okay. Now, when you multiply those two, what are you going to get? A JI, you're right. But then you're going to transpose that, so you're going to get a... No, when you transpose it, you get an IJ. Exactly. Now, remember B, okay, remember B, that was a KI, and the A was a JK, okay? Now, when you transpose the B, okay, let's back up. What if we had transposed the A? Then that would have become a JK. A KJ. And if you transpose the B, it would have been an IK. This would have been a KJ, that would have been an IK. Can you multiply those? No, you can't. So you can't just transpose them in order. What you have to do is reverse the order, because if you transpose this, you get an IK. Transpose this, you get a KJ. So when you multiply those two together, you get a IJ, and that's what you got down here. So yes, this makes sense dimensionally, and the others would not. So you have to reverse the order of B and A, okay? Now, they they did the first one, which is a really easy one, but again, read through the proof, and you'll see it's pretty straightforward. Okay. Now, properties 2 and 4 can be generalized to cover the sums and products of any finite number of matrices. So, let me do a little bit of fiddling here. Okay. 2 and 4. So let's take some room for 2 here. That is the title of it, but I need room to write, so I'm going to erase that. You could extend this 2 to be A plus B plus C plus as many as you wanted to do, transpose, and then guess what that would be? A transpose plus B transpose plus C transpose. So you can have as many terms, matrices as you want added together. The rule doesn't change. And by the way, we didn't do our dimensions on this. If you wanted that A to be a JK, like you did before, right? What size would B have to be for you to add it? It has to be the same. It has to be a JK. So when you add two JKs, you get a JK. And this would be, no, I'm sorry, yeah. You add them, you get a JK. And then when you transpose them, you get a KJ, right? Well, then this is a JK. That's a JK. I'm sorry, a KJ, and that's a KJ. I forgot what we named it. KJ, when you transpose that, and V had to be the same, so that's a KJ. Add those together, you get a KJ. And sure enough, you get the dimensions work every time, as long as they're properly dimensioned. A, B, and C have to be the same dimensions, else you can't add them anyway. And then when you transpose them, and when you add them, you get the same dimension. When you transpose, you reverse the dimensions. And then if you transpose A, you reverse. Transpose B, you reverse. Transpose C, you reverse. Add those together, you get reverse. So yeah, that works. Now let's see about the number 4 there. Let's erase that one, or at least the verbiage out. Ooh, that didn't erase, did it? There we go. Okay. What do you think happens if you started with A, B, C transpose? What you reckon its result will be? What's that? Okay, and what would that be? C transposed, B transposed, A transposed. Exactly. So however many products you have, you just reverse them in, multiply them in the reversed transposed order. Okay. Now there's a little remark here. Remember that you reverse the order of multiplication when forming the transpose of a product. That is the transpose of AB, AB transpose of B transpose A transpose. And it's usually not equal to A transpose B transpose, because quite often you can't even do A transpose B transpose because of dimensions. All right, so let's do example 9 and see what we get. Show that A, B transpose and AB transpose are equal. So here's our A good old 3 by 3. 2, 1, negative 2. Negative 1, 0, 3. And 0, negative 2, 1. Okay? And here's our B. 3, 1. 2, negative 1. And 3, 0. All right. Now, what we're trying to show is AB transposed is equal to what? A transpose. Okay. That's what we're trying to show. So the first thing we've got to do is multiply AB. So let's do AB. What size will that be? Okay. Yeah, this is a 3 by 3. That's a 3 by 2. So it's going to be 3 by 2. All right. You tell me what to write down. Yeah. Okay, is that your final answer? I couldn't hear. Okay, and what did you say? 2? Is that what you said? Yeah. Okay, because you got 6 plus 2 is 8 minus 6, so sure enough that's 2. Next. Which way are you going? Across or down? Across, okay. One. I want you to say 1. Okay. Six. Negative 1. Negative 1. 2. Okay? And one more thing we've got to do is transpose that. So AB transpose is what? 2, 6, negative 1 across. Across. Got it. Okay? Now, what we want to do next is multiply B transpose times A transpose. What's B transpose? Is what? 3, 2, 3, 1. Okay, that's B transpose. What's A transpose? Got it? Okay. Let's see what happens if we multiply, or can we even multiply those? What have we got? 2 by 3 by a 3 by 3, so that's going to give us a 2 by 3. Okay, that's sounding okay, because that's what we got before. Let's see what we get. Two. 6. Negative 1. Okay, 1. Negative 1. 2, yeah. And let's see. Looky here. Those are indeed exactly the same. Okay. So we showed that for those two matrices. All right. Good deal. And even the book got it right. Good for them. Wow. Okay. So let's go on and do example 10. Any questions before I delete this? Okay. All right, example 10. For this matrix, A, 1, 3, 0, negative 2, negative 2, negative 1. Find the product A transpose. Okay, for this, find A transpose and show that it is symmetric. All right, that's not too bad. Thought it was going to be a lot worse than that. So I'm going to just go on and delete that. I thought there was going to be more to find, so I needed to write it all down. What we're looking for is A transpose. Well, I already got A written down. What would be A transpose? Okay. Okay. Question. Can you even do that? Why? 3 by 2 times a what?
No, 3 by 3.
3 by 3. So you should get a 3 by 3. All right, we'll try that and see if it works. Goodness, my eye hurts. All right. Get started somewhere here. Okay? What's that? 10. Okay, I'm good. Sorry, I can't hear. Next. Negative 6. Next. Negative 5. Next. Negative 6. 4. Yeah, 2. Goodness, my eye hurts. Next. -5. 2. 5. Okay. We found what A transpose is. There's A. This is A transpose. And we see that it is a, what kind of matrix? Symmetric. It doesn't matter what the diagonal is, but the off diagonals are identical. Okay? Mirrored across the diagonal, they're the same. So it is a symmetric matrix. So see the one we had earlier, they're all ones down diagonal. Didn't have to be. To be a symmetric matrix, that's all it takes. Okay? Show that it's symmetric, it's true enough it is. Oh, and here's something else. Remember what we said about symmetric matrix? The transpose of a symmetric matrix, didn't we say this? Maybe we didn't. I keep forgetting. No, I guess we didn't. We showed it earlier, but that the transpose of a symmetric matrix is a symmetric matrix, okay? Is itself. Because if you transpose this, what you get, look at this, that row is that column, this row is that column, I mean, I've said it backwards. This column is that row, this column is that row, and this column is that row. Yeah, so transpose of that is itself. That's true about every symmetric matrix. So, when you multiply a matrix by its transpose, you're going to get a symmetric matrix. And frankly, you can always do that because 2 by 3 will always multiply by 3 by 2. And m by n always multiplies by n by m, whatever those sizes are. Now, the property demonstrated in example 10 is true in general. That is, for a matrix A, the matrix A times A transpose is always symmetric, and the matrix A transpose A is also symmetric. But are they going to be the same matrices? What if you did those in the reversed order? Multiply this one over here and that one over there. What would you get? Why wouldn't that be? They would be a different size. This would be a 2 by 3 by 3 by 2. That would be a 2 by 2. It'll still be symmetric, but it's definitely not going to be the same symmetric matrix. So that's the thing to watch out for. Okay? Linear algebra applied. Information retrieval systems such as internet search engines make use of matrix theory and linear algebra big, big, big time. Okay? In fact, I suggest to you, and no one knows what it is because it's very proprietary, but Google, what made Google Google is they came up with a search engine that was far superior to anything anybody else had, and that's what made Google the company it is today. Is their two founders, one of them was the linear algebraist, the other was a marketer or something like that, but they worked really well together. And no, I think one of them had the concept, the other one did the nitty-gritty dirt work, you know, and they got it put together as a team, and they did. Okay, that finishes 2.2. Homework exercises here. Any of the odds 1 through 5. Any of the odds 7 through 11. Do number 13. Do any of the odds 15 to 19. Do 21. Do 23. Do 25. And do 27. And then you choose any of the odds 29 to 33. Do 35. Do 37. Do either 39 or 41 or both. That's up to you. And again, either 43 or 45 or both. That's up to you. I'll just say now, 45 is a lot more involved than 43, so I'll let you decide what you're going to do with that. Then goodness, my eye hurts. It hurts to read. 47 is a true-false question. Don't expect to see too many of those on tests, but still a good thing to think through. 49 is a pretty good one to think through. Try to do 51, okay? I know that seems like it's outrageous, multiplying that matrix by itself 19 times. It's going to take up a lot of time unless you figure out an easier way, okay? Try to do 53. 55 is using polynomial functions, so that would, I think it's sort of oh man, a good one to think through. Man, this hurts. And then you got a bunch of either guided proofs or proofs, and I'll let you decide how many and which of those you want to do. Any of the odds, 57 to 65. Yeah, okay. I don't even remember. Do they have these answers in the back? This is 2.2. I can't remember if they do that. 2.2. No, they don't. So you're not required to do those. The proofs, that's what they say in the back, 57 through 65 proofs, and that's all they do. So if you want to think through those, you can, but I wouldn't get too bogged down. If there's something you feel like you need to know about them, ask. Okay? Now, again, they've introduced to you the concept of the symmetric matrices, but they now introduce another kind of matrix, which is called a skew symmetric matrix. Okay? And they do give the definition there. A skew symmetric matrix is when a symmetric matrix is when A transpose is equal to A. A skew symmetric is when A transpose is equal to exactly the opposite of A. So, you can play around with 67 and or 69, up to you. Some more proofs there, 71 or 73 if you want to, but you don't have to. But then 75 is a good one to think through. You don't want to get too bogged down with it, but think through that. All right, new concept here, and this is a lot of what we've been heading for, okay, is the inverse of a matrix, okay? Section 2.2 discussed some of the similarities between algebra of real numbers and the algebra of matrices. This section further develops the algebra of matrices to include, the solutions of matrix equations involving matrix multiplication. So they start with an algebraic expression. AX equal B. This is just simple algebra. AX equal B. Okay? How would you go about solving that? Solving for X. Figuring out what X is. A and B are just numbers. Whatever they happen to be, they're just numbers. X is your variable. Divide both sides of the equation by A, and you get X is equal to B over A. Now, how's another way we could express 1 over A? Second, yes, the inverse. That'd be A to the minus 1 times B, right? Okay. Now, when we do a number or a variable and put a minus 1 as a subscript, what we're talking about then is a reciprocal. 1 over X, 1 over A, okay? Now, remember when we did inverses before, right? We did that earlier, okay? But remember that minus 1 doesn't mean 1 over, okay? That means inverse. But guess what? The representation of it looks very, very similar, okay? So let's get to the definition for the inverse of a matrix. Now, I think I'll go and erase this just so it won't be clagging up the room. I got to sneeze, sorry. Y'all awake? Okay. Oh man, sorry. I can feel that one coming. That doesn't do anything to help my eye either, by the way. Now, let's say we have a matrix A. What is required for that matrix to have an inverse? First requirement. Say again? Good old L7, remember? Oh, y'all forgotten already. Gotta be a square matrix. Gotta be a square matrix. And they're calling this n by n. Okay? Gotta be a square matrix, or else you can't even begin to have an inverse. So this matrix A is invertible. Okay? Now, another word for that is non-singular. Okay? Now, why they, well, there is a reason. Okay, either invertible or non-singular. When there exists another matrix, when there is another n by n matrix, okay, B, we'll call it, okay, such that, okay, AB is the same as BA, and that is your identity matrix, n-sized identity matrix. Okay. Now, we did this before, didn't we? I can't remember. I've taught this course so many times, you get crossed up when they introduce this. Yeah, no, we did the, no, I guess we haven't. Let's go back and just, no, I guess we haven't. This is the first time we've introduced it, I guess. Is that right? I guess that's true. I was thinking we had already done that. Okay. That's what it means to have an inverse, to be invertible or non-singular. If there is some other square matrix, same size, yeah, is it time? Oh no, how sad. You're supposed to, your voice was supposed to be breaking up when you said that. Okay, never mind. Okay. All right, we'll pick up and go from there. We'll pick up with this definition of an inverse matrix. We'll start there again. All right. And I don't think we did enough for homework exercises there, so we'll start on 2.3 next time. What's that?
I might not make it to
What? Okay.
I'm gonna try to make it, but
Right.
I gotta do my taxes.
Oh, I see. You got to April 15th, you know.
Well, it's like
He's trying to get that refund.
no, they put like an appointment on me. It's like
Oh, I see. Okay.
I tried to.
Yeah, I know.
I tried my best to get it to like
Right.
Tuesday or something.
Yeah, I know. I'm just giving you a hard time. Okay, we always put off ours till almost to the very end, just because we almost always owe money and we'd rather wait till the end to pay it. But yeah. All right, good deal. We will see at least one of you next time later in the day, but hopefully both. So we'll see. Yeah, good luck with them.